Hello guys and welcome to a new video in physics. In this video we will talk about module 10, lesson 1, which is about work and energy. The focus question for this lesson is what is energy? And we will know the answer of this question in this lesson. The new vocabulary that we will learn in this lesson is work, joule, energy, work energy theorem, kinetic energy, power, and watt. Review vocabulary, law of conservation of momentum. In previous lesson, we had law of conservation of momentum, and we said that it states that the momentum of any closed isolated system doesn't change. The first subject that we have in this lesson is work. When a net force is exerted on an object while the object moves a certain distance, so the object will be accelerated and its velocity will increase. If you combine Newton's second law, F equal to ma, with the equation for motion 2ad equal to v final square minus v initial square, and rearrange the equation, you obtain Fd equal to half mv final square minus half mv initial square. The left side describes an action done to the system. So a force F was exerted on an object while the object moved a distance d. So F represents the force and d represents the distance. When a force is applied through a displacement, work W is done on the system. We can make a definition for the work, which is the definition of work is a force applied through a displacement, and its symbol is W. The SI unit of work, SI means the System International of Units, of work is called a joule, and its symbol is J. 1 joule is equal to 1 Newton dot meter, because we know that the Newton is the unit of the force and meter is the unit of displacement. So 1 joule is equal to 1 Newton dot meter. The equation W equal to Fd holds true only for constant forces exerted in the direction of motion. An everyday example of a force exerted perpendicular to the direction of motion is the motion of a planet around the Sun. If the orbit is circular, then the force is always perpendicular to the direction of the motion. The speed of the planet doesn't change, and so the right side of the equation is zero. Therefore, the work done is also zero. Only the component of the force that is the direction of motion F cosine theta does work on the system. And here we have the law of the work, which is W equal to F d cosine theta. W equal to F d cosine theta. So when we have the theta here, if the theta was perpendicular, which is 90 degree, so we will not have work, because the cosine of the 90 degree, for example, if we have here we have theta equal to 90 degree, so that will be W equal to F d cosine 90 degree. The cosine for 90 degree, that's equal to 0. So 0 multiplied by any number that will equal to 0, so the work will also equal to 0. The work is equal to 0 when we have a perpendicular theta. Now we have a question. When a club head strikes a 46-gram golf ball, the ball picks up 43 joule of kinetic energy. The force of the club head on the ball is not constant, rather in the short collision time of the club head and ball. The force builds to a peak and then diminishes, but for the purposes of the calculation in this problem, assume that the average force magnitude, which you can treat as constant, equals to 2300 Newton. Over what distance is the club in contact with the ball? So as we learned in the beginning, we should we should write the noun and the unknown in this question. So here we have the mass of the ball, which is equal to 46 gram. Here we have the mass of the ball, which is 46 gram. And also we have the force, which is equal to 2300 Newton. And we have the energy, which is equal to 43 joule. We need to calculate here over what distance is the club in contact with the ball. So we need to find the distance, which is it's simple is d. So we have our law, which is W equal to F d cosine theta. Because here we have the movement, the distance that will, the distance of the ball in the same direction with the force, so the angle it will be 0. So the cosine theta for 0, that's equal to 1. And our law will be W equal to FD because it's multiplied by 1, and we can cancel it because here we have just 1. So when you need to find D from the equation, D will equal to W over F because we need to calculate D, the distance, D equal to W over F. W, the work, is exactly the same with the energy. In any question that you will see in your book, when you see energy, it's the same for the work. So delta E over F. Delta E, which is 43 joule over 2300 Newton. The final result will be 1.9 times 10 to power minus 2 meter. The unit here, we have it in meter because we need to calculate the distance. Now we have another problem. How much work is done in pushing a tall box 15 meter with a force the magnitude of which is 4 times 10 to power 2 Newton? That is applied slightly upward at an angle of 10 degree from horizontal. So in the beginning, we will write the noun and the unknown for the question. And here we have the sketch for the problem. The sketch is, here we have a man is pushing the box. And in the question, he told me from horizontal. So the movement will be in this direction. And here we have the angle is equal to 10 degree. So the angle between the force and the distance is equal to 10 degree. The noun that we have in this question is F equal to 4 times 10 square Newton. So that represents F, which is the force. D, we have it in the question, which is a 15 meter. We can write it with the unknown. And theta, we have it, which is equal to 10 degree. And we need to calculate the work. So we have a law which is W equal to F d cosine theta. F 4 times 10 square Newton multiplied by the distance which is equal to 15 meter cosine 10 degree. By the way, here we have cosine 10 degree that's equal to 0.9. Cosine 10 degree that's equal to 0.9. So when you multiply 0.9 by 15 by 4 times 10 square, that will approximately equal to 5,900 joule. Now we have example problem number 1 in the book. A hockey player uses a sticky to apply a constant 4.50 Newton force forward to a 105-gram puck sliding on ice over a displacement of 0.150 meter forward. How much work does the stick do on the puck? Assume friction is negligible. So in the beginning, we will write the noun and the unknown in this question. The noun that we have in this question, we have 4.50, which is represent the force, because here we have the unit in Newton. So the force is equal to 4.15 Newton, 50, sorry, Newton. And also here we have 105 gram. This is the mass, m equal to 105 gram, and the displacement that we have in the question, which is equal to 0.150 meter forward. Now we will write the sketch for this question to know the angle. So because here we have the force and the displacement in the same direction, so the angle will be 0. Theta will equal to 0. And we need to calculate W, which is the work. So we have a law which is W equal to F d cosine theta. F, we have it in the question, equal to 4.15 50 Newton, and we have d displacement, which is 0.150 multiplied by cosine theta. Theta, here we have it 0, so cosine 0, that equal to 1. So 4.50 Newton multiplied by 0.150, that will equal to 0.675 Newton dot meter, which is the unit for the work. Or we can say that 0.675 joule, which is also the unit of the work. Now we have question number 1 in practice problems. So refer to example problem 1 to solve the following problem. A. If the hockey player exerted twice as much force, 9 Newton, on the puck over the same distance, how would the amount of work the stick did on the puck be affected? So if we doubled the force, how would be the work? So work equal to F d cosine theta. So because here we know that already cosine theta is equal to 1, so our law will be W equal to F d. Now we will write the numbers, which is the F equal to 9 multiplied by d, the distance from previous question, which is 0.190. The final result for the work was 1.35 joule. And this is the final result for the work. This is for question A. Now we will talk about question B. If the player exerted a 9 Newton force, but the stick was in contact with the puck for only half the distance, which is 0.075 meter, how much work does the stick on the puck? So here we have the double or twice for the force, and we have a half of the distance. So we will have the same result for previous question, because here we have the double for F and a half for D. So we will have the same result. And you can try it by multiplying 9 by 0.075. The result will be 0.675. Question number 2 is the same for question number 1. So I will not solve it because it's the same and with the same law. Question number 3 is an important question, so we will solve it. Question number 3. A rock climber wears a 7.5 kilogram backpack while scaling a cliff. After 30 minutes, the climber is 8.2 meters above the starting point. A. How much work does the climber do on the backpack? B. If the climber weighs 645 Newton, how much work does she do lifting herself and the backpack? So in the beginning, we should write the noun for the question, which is here we have the noun. We have the mass, which is equal to 7.5 kilogram. Also here we have the time, t, equal to 30 minutes. The climber is 8.2 meter above the starting point. Here we have the displacement, which is equal to 8.2 meter. The question is, how much work does the climber do on this pack? So our law, it should be W equal to FD. But here we don't have F in the noun. But we know that F, I will write it here, F equal to M multiplied by G. So F equal to M, which is the mass, which is equal to 7.5 multiplied by 10. It's approximately 10. And F equal to 75 Newton. By the way, F equal to M multiplied by G, that means the force equal to the mass multiplied by the ground acceleration. The ground acceleration, it's 9.8, but approximately we will write it as 10. So 7.5 multiplied by 10, that's equal to 75 Newton. And now we can solve the question, which is W equal to F. We have it now. This is F, which is equal to 75 multiplied by displacement. We have it in the question, which is 8.2. So W will equal to 615 joule. And this is for question A. And about question B, if the climber weighs 645 Newton, how much work does she do lifting herself and the backpack? So, because here we have the weight 645, the weight in Newton. So the weight is also represent the force. We can solve it just like this. Here I will solve it here. B that equal W equal to F D. So the work equal to the force. Here we have it, which is 645 multiplied by the distance, which is 8.2. So W equal to 5,289 in joule. And this is the solution, the final result for the work in question B. This is the challenge, is a homework for you, which is question number 4. Until here we reach to the end of our lecture. See you soon in another one, inshallah.